Last time, we talked about diffusion processes with accumulation, but everything we have talked about up until this point is dependent on the idea that the concentration is in equilibrium. However, most of our experience with diffusion is not in equilibrium. When I drop dye into water, I see that the concentration of dye changes as a function of time. This is a great example of where synthesis of your physical knowledge into analytical reasoning and computational skills plays a really important role in your engineering judgment, because you simply have to be able to think about what you expect prior to finding a solution. Today we are going to develop a way of modeling time-varying diffusion. To make the development as simple as possible, we are going to assume that there is no accumulation, but that the concentration is allowed to change in time. Let's look at our example of a tank with fluid and some chemical in the tank. So again, we have a tank. We have x1 and x2. x1 and x2 are separated by dx. We have v is equal to a dx, and we have flux at x1 coming in to that volume, and flux at x2 going out of the volume. So we still have the same basic components as before. A very small volume V with flux in and out of the volume. Now, however, we are going to allow the mass in that volume to change as a function of time. The mass in a small volume is the concentration times the volume. So C of x times V, which is equal to C of x times A dx. And that's the mass inside the volume. The only thing that could lead to the mass changing in that volume is if the flux in and the flux out are not the same. Hence, d dt of C of x A dx, so this term is the mass, is equal to f of x1 minus f of x2. Now that is equal to d minus d times dc dx1 dx times a minus d dc at x2 dx times a. And all of that is equal to d times dc of x2 dx minus dc at x1 dx, all times a. I have used the partial derivative notation for the derivative of c with respect to t and the derivative of c with respect to x. This equation implies that we can divide by a and divide by dx. Recall that we did this before in lecture 14, but without any real reason or explanation. Taking the limit as dx goes to 0, we get that the time derivative of c is equal to d times the time derivative of c with respect to x. So what we get is dc of x dt is equal to d times dc of x dx squared. This is called the time-varying diffusion equation. Note that there are both derivatives with respect to time and with respect to position. Because of that, this equation is called a partial differential equation, or PDE for short. This is why I used the partial derivative notation earlier. PDEs are often very challenging to solve, and in general we cannot expect to have e to the ht with sines and cosine terms showing up as solutions. Also, the initial condition for this problem is a curve rather than a number. That is, the initial condition might look like C of x could look like something like this. So there is a lot of chemical in the left and less in the right part of the tank. If there is no flux of chemical into or out of the tank, we might expect as time progresses this non-equilibrium initial condition to approach a solution where C of x is flat and the chemical has diffused everywhere equally. However, if we make two assumptions, we can make a lot of progress. First, assume that the tank is infinitely wide, so x is between minus infinity and infinity. This is reasonable even if the tank is simply very large. And secondly, assume that the chemical starts out all in one place, perfectly concentrated at a particular position x. These assumptions model the situation where you drop a single drop of chemical into a very large tank, and we are now asking how that single drop will diffuse through the tank as a function of time. If I drop just one small drop of milk in my coffee cup, it takes a while for the walls of the coffee cup to matter in the diffusion of the milk. It turns out that with these assumptions, we again get an analytical solution that is of the form of an exponential. We get c of x t is equal to a times 1 over the square root of 4 pi dt times e to the minus x squared all over 4 dt. This equation solves the diffusion equation for any constant a, which will depend on how much chemical there was in the drop. Some things to note about this equation include that at t equals 0, the coefficient of the exponential term is infinite. This is why we assume that the chemical is all in one place at time t equals 0. After time t equals 0, the coefficient multiplying the number goes down, and the curve c of x becomes broader as the chemical diffuses away from the point it started. How would you verify that c of x and t solves the differential equation? Plug into the time-varying diffusion equation and find out that the time derivative of this equation is equal to d times the second derivative with respect to the position x. Verifying that this function is a solution is something you will consider more in the exercises following this lecture. You might notice that this function is related to the Gaussian distribution. This will turn out to be useful in the demonstration that we are going to do for chemical diffusion. Lastly, notice that the time-varying diffusion equation is in fact a linear differential equation. That means that it satisfies the principle of superposition, which means you can take several of these exponential curves and add them together in order to construct a more complex solution involving chemicals starting out in several positions x in the fluid. What should you remember from today? You should remember that when a diffusion process is not in equilibrium and there is no accumulation, the time-varying diffusion equation provides us with a way of approximating how the chemical will diffuse over time throughout the fluid. However, this model requires two relatively strong assumptions. Not all systems, even engineering systems, will satisfy the assumptions we made.